Okay, so welcome everybody to today's presentation. Thank you for joining, and thank you, Dr. Stephan Guenther, for attending today's session. Today, our webinar is going to be talking about DOE-based optimization of electrical machines. This is a multi-objective optimization approach, discussing the importance of multi-objective optimization and showing at how the people at IAV deal with these types of optimization problems. I will be giving the ball quickly to Dr. Stephan Guenther. He can give a quick introduction about himself, and then we can start the session.
Okay, thank you. Hello to everyone. My name is Stephan Guenther. I work at IAV as an e-machine design engineer within the e-traction department. I received my diploma and doctoral degree in electrical engineering at the Dresden University of Technology in Germany. And I now have more than 12 years of experience in research and development related to e-machine topics. And my main research interest deals with the large-scale optimization of e-machines. So that's pretty much a topic we are going to introduce and discuss in today's webinar.
Okay, thank you. I will be starting the presentation right now. Let me know if you notice any technical issues in the beginning, because usually they tend to pop up.
Thank you very much for the introduction. Today, I would like to present an optimization process for electrical machines based on the so-called design of experiment approach, or in short, DOE. We at IAV use this in-house developed process mainly for the design of e-machines used. You actually need to start the presentation.
Do I need to switch?
In different automotive applications.
Maybe
So
you just end the slideshow and then you go to slideshow. Yes. Okay, wait, let me see. 1 second, I'll figure it out. Share. Okay, we're sharing this.
I have structured the presentation as follows. At first, I would like to provide a short introduction to the different optimization.
I think there's an issue with the sound. It keeps cutting off. Okay, wait. We can figure this out quickly. Share.
Approaches according to the state of the art, including the.
Okay. I'll try to restart this.
Thank you very much for the introduction. Today, I would like to present an optimization process for electrical machines based on the so-called design of experiment approach, or in short, DOE. We at IAV use this in-house developed process mainly for the design of e-machines used in different automotive applications. So for instance, traction motors of electric vehicles or starter generators. I have structured the presentation as follows. At first, I would like to provide a short introduction to the different optimization approaches according to the state of the art, including the benefits of the DOE approach. The DOE process itself is split into 3 parts: the pre-processing, the simulation, and also the post-processing part. The DOE pre-processing deals with the preparation and setup of the DOE process and includes, for instance, the definition of the application and variable parameters, the generation of the DOE designs, and also the setup of a parametric JMAG model. Within the simulation part, the multidimensional solution sets are calculated based on FEA using JMAG under additional consideration of meta models. And the post-processing part deals with the derivation of optimal designs. Here we use a data visualization tool which helps us to figure out the best fitting designs for a given application based on filter setups and a benefit analysis. And last but not least, I would like to give a brief outlook for the e-machine optimization process. The optimization approaches can be divided into two groups. The first group, the deterministic algorithms, are the classic approach for many optimization problems. The derivation of the search direction is gradient-based. We typically need an analytical description of the relations in between in and output parameters. There's a high risk of convergence issues if the starting points are chosen unfavorably. And for complex e-machine optimization, it is usually not suitable as a standalone approach due to the missing full analytical machine description. The second group, the stochastic algorithms, are based on stochastic decisions. There's no analytical relation needed, and these algorithms are usually quite robust, easy to implement, and just need a few control parameters. In general, more designs are needed before reaching a sufficient convergence in contrast to the deterministic approach. Typical examples are the Monte Carlo method simulating annealing differential evolution and also the well-known particle swarm optimization. Our approach, the design of experiments, or in short DOE, is not an optimization by definition. It's rather about the conducting of a set of predefined experiments in order to derive the relations between in and output parameters. The procedure aims at generating a response surface for all involved parameters and samples the entire search space in contrast to optimization algorithms. So why is the DOE-based approach preferred by IAV? When we start a new development project, we typically define the specifications for the e-machine and system characteristics together with additional optimization constraints and objectives for the e-machine. However, in most projects, not all parameters can be freezed or even prioritized accordingly in advance. This is in particular an issue for early design stages and prototype developments. The flexibility to easily react to changed specifications or optimization setups in a later design stage is always required by the applied optimization process. When we just use standalone optimization algorithms such as deterministic or stochastic processes, we have several drawbacks. These kind of optimization algorithms usually need a well-defined optimization setup, including freeze specifications, constraints, and objectives. But after evaluation of the optimization results with the customer, it is usually required to rerun the optimization procedure, sometimes for several times, for just slightly adjusted optimization setups in order to figure out hidden relations and sweet spots. This means that we have the enormous computational effort several times. If we apply the DOE approach, we have in contrast the computational effort just once, because then we have afterwards the complete search space covered. The optimization setup can be easily adjusted, sometimes even during a customer meeting, in order to find the best fitting design for the given application without rerunning the entire simulation. And we can adjust the optimization setup several times and see instantly the outcome based on this new setup. And what is also possible, we can also run additional optimization algorithms on the DOE response surface in a quite fast manner. So the first step within the DOE process deals with the definition of the application and the reference design. It is very important to gain an understanding for the application based on the specification for the e-machine and the system. We usually discuss important objectives and constraints with the customer in advance. These discussions include, for instance, the peak performance, the continuous performance, costs, magnet mass, winding types, cycle loss, and so on. So we have a huge variety of different parameters we need to look at. In general, it is also beneficial to have a reference design for the DOE optimization. This is preferred but not compulsory, but an existing design helps us to define a proper search space for the optimization. This design can, for instance, result from a concept phase based on a conventional e-machine design process, or it is already given by the customer. In most cases, the reference designs already meet many specification criteria, but typically lack in fulfilling all the required objectives and constraints. And that's why we need a detailed optimization. Based on an existing reference design, the variable parameters with lower and upper limits can be defined. These parameters can be continuous, for instance, the stator inner diameter or the magnet height, or they can be discrete, for instance, the number of turns per coil. As said before, the reference design is then used as an orientation to define the search space. On the right-hand side, you see a typical setup with 12 variable parameters with the reference design values and the corresponding lower and upper limits. It is also of interest to see the correlation in between the number of dimensions and the effort and computing time. Here you see three different typical setups. The first one would be a local optimization with a free stator or freezed rotor. Here we have just a small amount of dimensions and also a small computing time. A more typical application would be to have a full machine optimization with simple rotor topologies, such as single V layers. Here we have around 12 to 15 dimensions with a medium effort. And having more complex rotor topologies means we easily end up having more than 20 dimensions with a large computing time, because much more DOE designs are needed to cover the search space in a sufficient manner. The generation of the DOE designs based on the defined search space is based on a random design distribution. In general, we also add additional complex constraints in advance in order to have a good distribution of the designs within the search space. These constraints help us to avoid the time-consuming calculation of so-called bad designs, which can be excluded prior to the FEA calculations. Examples for such constraints can be current densities, the magnet mass, or also conductor dimensions for instance, hairpins. Below you see an example where we have the conductor width and the conductor height, and we also have a constraint for the current density. And based on the current density constraint, we also have the reduced search space with more dense design distribution. So how many DOE designs are actually required? It is well known that this depends on the number of dimensions, and from our experience you see here a typical behavior. When we have, let's say, a typical optimization setup with 12 dimensions, it is beneficial to have, let's say, more than 1,500 DOE designs in order to have a good search space coverage. So in total, it's better to have more designs, but it is also more time consuming. Below you see an exemplary DOE input table where we have for each row we have one e-machine with a corresponding index, and then we also have here the input parameters that are variable. The next step deals with the setup of a parametric JMAG model. This is done by using equations and CAD parameters, and the main priority here is on having a low failure rate due to, for instance, geometry conflicts. We also use an automatic coupling in between JMAG and MATLAB, and we have different MATLAB processes, and these processes generate the input parameters, transfer them to JMAG, then we run the different JMAG calculations and export the results back to MATLAB. At IAV we have several JMAG MATLAB processes. The so-called fast EMAG process is mostly applied for large-scale DOE optimizations because it represents a good trade-off between simulation time and accuracy. The main focus of our DOE simulations is on the electromagnetical behavior, and thermal and mechanical characteristics are usually derived by using additional analytical approaches in order to save computation time. And these domains are typically addressed in final e-machine design stages in more detail. So the fast EMAG process calculates the e-machine maps based on steady state calculations in order to derive the MTPA optimal currents. We usually have a sinusoidal current supply, and we also have usually no rotor skewing in order to save computation time here. For selected operating points, several transient calculations are performed, including basic loss analysis. Then we also have the standard map calculation process we usually apply for selected designs after the optimization. Here we do transient FEA-based calculations for the entire torque speed operating area, including rotor skewing, and we have a loss analysis for all the operating points. And of course, it's also possible to apply more advanced map calculations. Here we have also transient FEA-based calculations for the entire operating area, including, for instance, BWM supply, rotor skewing, manufacturing influences, and also advanced loss analysis, for instance, with AC losses in round wires. And this process is usually applied at the end of the design process, so in the final design stage, and also for the evaluation of special effects. After having finished all the FEA-based calculations for the e-machine designs, we are able to generate a so-called DOE table with all the input and output parameters for each considered EM design. What you see below is an excerpt from an exemplary DOE table where you see the index numbers for each DOE design. Then you see here all the input parameters. In this case, we have 12 input parameters in total. And on the right-hand side are all the collected output parameters for all the designs. In this case, we have just a few output parameters, but in general, we usually have much more parameters in this case. And this database is actually used to generate an additional meta model. At first, I would like to clarify why we are using a meta model and why it is important. The coverage of the multidimensional search space by just FEA-based DOE designs is usually not sufficient. A typical example would be to have 2000 DOE designs distributed within a 15-dimensional search space, and this would lead to huge unknown areas in between these discrete designs. And the consequence would be that it is hardly possible to find an optimal design. That's why we are using a meta model, and our approach is the so-called Kriging method, which is commonly used in geostatistics, for instance, to predict the material grades in mining based on discrete drilling. It is a fast analytical approach for the prediction of the behavior at unsampled locations based on the known values in the neighborhood. And of course, this method can also be applied to the e-machine optimization process as well. The advantage of the Kriging method is that it also provides an estimation error for each new sampled location in order to evaluate the model quality. And based on that, it is possible to add more DOE designs if the estimation quality is too low. And using this Kriging meta model, the solution set can be easily extended from a few thousand original DOE designs to up to more than 1 million additional Kriging designs, and that all within a reasonable computation time. Below you see two examples where we have the dark blue original FEA-based DOE designs, and after application of the Kriging method, we were able to increase the number of solutions by a huge amount. You see the Kriging designs in a light blue color. After having derived all the FEA-based designs and Kriging designs, it is now needed to figure out the best fitting designs for the application. For this, we use an in-house developed IAV tool for the fast data visualization of large data sets. And the first step here would be to define a filter setup based on different constraints and filter criteria. Here below you see an example where we have defined several constraints, and also you see here the corresponding numbers. And based on such a filter setup, it is possible to reduce the number of viable solutions. In this case, we have applied this filter setup, and then you see the gray designs here in this case. These designs are removed because they do not meet all the filter criteria. And what it is remaining are the light blue Kriging designs and a few FEA-based designs. And as you know, the Kriging designs still have the estimation errors, and that's why we typically select these remaining Kriging designs and recalculate them based on the FEA process just in order to eliminate the estimation errors. After having applied the filter setup, we have several remaining designs, and the final task here is to figure out the best fitting design, so the optimal one. And for that, we do a benefit analysis where we at first define the objectives and the corresponding weightings. And it is also possible to define several objective setups. And based on that, we do a ranking of the designs corresponding to their benefit value. And below you see a typical exemplary setup for the objectives. In this case, we have 4 objectives and the related weightings, and the result is then the rank of the design with their benefit value. And in general, we then select the best design with the rank number 1 and the highest benefit value. And the selected final optimal designs are transferred to the final design phase. And in this phase, we usually analyze the designs a little bit more in detail before the prototype is built. And the required simulations can cover several things. For instance, the mechanical rotor strength analysis by FEA. What we usually also do is then the advanced map calculation corresponding to our process, where we also look at the AC loss, PWM, and manufacturing influences. What is also usually needed is the thermal analysis of the peak and continuous curves, and sometimes also an additional 3D analysis of several end winding influences that might be AC losses and also the end winding leakage inductance. At the end of the presentation, I would like to give a short outlook regarding the DOE approach. In general, we always need to figure out a good trade-off in between model complexity and simulation time. We currently have the following setup for the electromagnetic simulations. We have transient FEA for selected operating points, but typically without rotor skewing, and usually also 2D models. The mechanical and thermal simulations are usually done by analytical approaches within MATLAB. So this is the current status with a reasonable computation time for large-scale DOE optimization. Of course, it's also possible to add several features. For instance, having a full map transient FEA for the electromagnetic simulations with rotor skewing and maybe even 3D. And it is also possible to add mechanical simulations based on transient FEA and thermal simulations based on larger thermal resistance networks. But this added model complexity leads to larger simulation times, and it is therefore actually too large for large-scale optimizations. But in future, we expect to be able to handle this complexity, but at a smaller simulation time by having, for instance, more computing power and process parallelization, improved meta models, which might lead to less designs, and also having a more efficient multiphysics FEA modeling. I hope you enjoyed the presentation. Thank you very much for your attention, and I am now available for questions.
Okay. Yeah, I think we have the present. Thank you, Dr. Stephan, for this presentation. We will be taking questions right now. If anybody has them, please feel free to put them in the chat. If anybody has any question, but I can start, at least from my side. I have a question regarding the consideration of harmonic effects from the PWM drive. How would you handle such Because usually when you're optimizing using a sine wave drive or a perfect case, an ideal current. So how would you, let's for argument's sake, you're optimizing for a sine wave drive, but you're not considering the PWM drive. So is that going to have an effect, and how would you handle that in the future?
Yes, that is indeed an issue. As you all know, the PWM simulation takes quite a lot of time. So putting this into the large-scale optimization usually doesn't make sense. That's why we prefer to do at first a global optimization just by using a pure sinusoidal current supply. And when you have narrowed down the search space, it's actually preferred then to do a local optimization. So just a few dimensions, and then you do not need that many DOE designs anymore. And then it's also possible to include the PWM supply.
Mm-hmm. And I see a question. Is there any example in JMAG so we can follow and learn how should we apply DOE for another EM? Well, JMAG does not use DOE optimization algorithms. We mainly use genetic algorithms. For optimization calculation, this method is mainly developed by IAV, or they're just using JMAG as a supplement where they're defining their optimization algorithm externally and then using JMAG as a transient solver. Correct me if I'm wrong, Dr. Stephan.
No, that's right. Yeah, exactly.
So basically in JMAG, you are usually doing a global search with a genetic algorithm. And from that, you are trying to converge onto your best possible solution. I have a question regarding the advanced map calculation. So this is usually the very last step where you've already optimized, like you've reached your very last step, and then you're trying to calculate the AC losses and everything. How many models are you evaluating at this point, or how many design variables are you taking into account?
For the advanced map calculation?
Yeah.
Well, actually, it's preferred that you maybe just have one design left, and then it's not an optimization anymore. It's more or less a verification, a recalculation, and maybe you have still some minor issues, but it's not an optimization then anymore, because doing all the advanced map calculations is very time consuming. So assume you add, for instance, the AC losses in the round wire, then you have to model each wire, and then it's really tough and time consuming. So that's not a thing from my perspective that you should add to a large scale optimization. Then it takes months to solve it. Yeah. So you actually need to figure out your application and problem. Then you start with the global optimization, and then you narrow it down. And if you did everything correctly, you just have one remaining design where you're pretty confident that everything works out when you build the prototype. And based on that, you do the advanced map calculations where you get all the effects included you might need, for instance, when you start controlling the machine at the test bench, for instance.
Thank you. We have another question. It says, do you think it would be better to do a sensitivity analysis to reduce the less input parameter, or like to reduce the input parameters or reduce the design space?
Yes, that is also possible. So sometimes we start, for instance, with 20 design parameters, then we have a first run, and then we figure out, okay, there are maybe 5 parameters which have a quite low sensitivity regarding our interested output parameters. And then it's up to us maybe to do a second iteration with fewer parameters. So this usually needs a little bit of experience. When you do this the first time, you probably remove the wrong parameters, I would say. So I would recommend at first to stick with more parameters if you do not your application that well. Yeah, because the benefit of the DOE approach is that you do all the calculations just once, and then you figure out the objective setup and constraints afterwards. So for instance, if you do the sensitivity analysis right at the beginning, you might figure out, okay, the let's say the tooth head height is not of interest for us because it doesn't affect, for instance, the demagnetization behavior that much. Then you might end up removing it. But doing further calculations and optimizations within the project, it might be starting to be of interest to have some harmonics that needs to be suppressed due to NVH analysis, and then you do not have this parameter anymore because you removed it right at the beginning. So my recommendation would be at first to have like a global optimization where you do not remove that many parameters. Yeah, you need to be sure that you put all the parameters that might be somehow of interest during the project within the search space.
Okay, we have one more question. Thank you for your presentation. I also have questions regarding map calculation. In case of traction motor, voltage utilization is of matter. There are trade-off based point torque capability and flux weakening capability to find optimal point in the circumstances. The phase advance shall be decided during large-scale design exploration. What was your strategy to deal with this?
Okay, I hope I get this right. So I guess at first you try to, you're actually asking how we get the phase advance angle that is optimal for the application. So at first we have a steady state map calculation. Here we do the calculations to get the relation in between D and Q axis current and the flux linkages and the torque. And based on that, the typical approach is here to use the maximum torque per ampere, so MTPA strategy. And based on that, we get for all the torque speed operating points the optimal DQ axis current. Yeah, and these DQ axis currents are then used to, for instance, calculate selected transient operating points. This takes a little bit longer. That's why we usually, for one e-machine design within the solution cloud, we usually have, let's say, 5-6 selected operating points that we are running as a transient simulation. And yeah, besides MTPA, it is of course also possible to switch the control strategy towards the ME, so maximum efficiency control strategy. So here we try to get for all the operating points the current combination that minimizes the total loss of the machine and within this operating point. Okay, and I think there was one more question before.
Yeah, are you able to consider demagnetization in DOE?
Yes, that is actually a pretty important point, and we usually do this calculation. What we do here is mainly the approach that we look at the active short circuit. And as probably most of you know, the worst case is when we switch the active short circuit at the peak torque at corner speed. Here we have a high risk of demagnetization, in particular at higher temperatures. And this is usually the setup we use. So within this operating point, we apply the active short circuit, and then we compare the torque right before and right after the active short circuit. And if we see some differences, we know at a glance, okay, due to the active short circuit, we lose maybe 1% of torque due to the demagnetization. So it, from my perspective, it should be included in most of the optimizations.